So today we are given a problem that fluid is flowing down the walls of a cylindrical pipe. And we want to verify through dimensional analysis that the Sherwood, Reynolds, and Schmidt numbers are the appropriate dimensionless groups needed to describe this problem. So what we must first do when completing dimensional analysis is to define the parameters that are used to describe this problem. So since we have fluid flowing down the walls of a cylindrical pipe, we need to know the density of the fluid as well as the velocity of the fluid flowing down the pipe and the viscosity of the fluid. And then with the pipe being cylindrical, the length in this situation will be the diameter. And then we know that since the fluid is flowing down the walls of the pipe, there will be some gas in the center of the pipe, and the fluid will be evaporating and diffusing into this gas. So we need to know the diffusion coefficient between the fluid and the gas, so DAB. And then finally, we need to know the mass transfer coefficient, Kc. So now that we have determined the parameters, we want to look at the units of these parameters. So we know that density is in units of mass over volume, so we want this in SI units, and that will be kilograms per cubic meter. Velocity is in units of meters per second. Viscosity is in units of Pascal seconds, and in SI units, this is kilograms per meter seconds. The diameter is in units of meters. The diffusion coefficient is in units of meters squared per second. And finally, the mass transfer coefficient is in units of meters per second. So we can see that all of these parameters incorporate either kilograms, meters, or seconds, or a combination of these three units, so that we can then create a matrix of the parameters along with the units, so kilograms, meters, and seconds. We can then use the exponents on the units of each of these parameters to create this matrix. So for example, for density, that's in kilograms per cubic meter. So kilograms is to the first power, so in the coordinate density in kilograms, we'll put a 1 for the first power. And then meters, it's to the third power in the denominator, so that it would be meters to the -3 power. And then there are no seconds, so seconds would be to the 0 power. And then we can do the same thing for the rest of these parameters. So for velocity, it's in meters per second, so meters to the first, seconds to the -1st. Viscosity, kilograms to the first, meters to the -1st, seconds to the -1st. Diameter, just meters to the first. The diffusion coefficient, meters to the second power, and seconds to the -1st power. And then finally, Kc, meters to the first, no kilograms, and seconds to the -1st. We will then use this matrix to determine the number of dimensionless groups that are applicable to this situation. So we can do this by taking the number of parameters n minus the rank of this matrix here. And we can solve for this rank in Python, so we'll do that right now. So now that we have created our matrix, we can easily determine the rank of this matrix in Python. So we first want to import numerical Python, which is called NumPy, and I'm going to abbreviate that as NP. And we want to import that since we'll be working with numerical matrix, with a numerical matrix in this situation. So then NumPy has a tool called matrix rank, which when you import a matrix, it returns the rank of that matrix, and it's within the numerical algebra toolbox. So to access this, it's NumPy, so np dot linear algebra dot matrix matrix underscore rank, and then we can import our matrix that we had. So the first line, we want to have brackets for each line in the matrix as well as for the whole matrix. So the first line is the kilograms line. So we have 1, 0, 1, 0, 0, 0. And then we'll separate this first line of the matrix with the second through a comma. So comma, and then we can indent and move on to the second line of the matrix, which is the meters line. So this is -3, 1, -1, 1, 2, 1, and that's the end of this line of the matrix. And then finally we have the second line. So that's 0, -1, -1, 0, -1, -1, and making sure that all of our brackets are lined up. If we hit Shift Enter, it returns the rank of the matrix, which is 3. And then we can use this rank of the matrix in our dimensional analysis. Now that we have found that the rank of this matrix is 3, we have 6 parameters minus 3, rank 3. So we have 3 dimensionless groups that are applicable to this problem. So we know that we're on the right track because we want to verify that the Sherwood, Schmidt, and Reynolds number are the appropriate dimensionless groups. And there are 3 of those, and we know that we have 3 dimensionless groups here, so we are on the right track. So now that we have found the number of dimensionless groups, we want to create 3 different equations that incorporate a core group of parameters and then one of the non-core group parameters. So I'm just going to create 3 arbitrary variables, pi1, pi2, and pi3. And then we need to determine the core group that we will use for this problem. So we can choose any 3 parameters that incorporate kilograms, meters, and seconds as the core group. So for example, we could choose a core group of density, velocity, and viscosity, since it incorporates kilograms, meters, and seconds. However, we could not choose a core group like diameter, diffusion coefficient, and mass transfer coefficient because it does not incorporate kilograms into the core group. So I'm just going to choose density, velocity, and viscosity as the core group, and I will write this in each of the 3 equations. So density, velocity, viscosity, density, velocity, viscosity, density, velocity, viscosity. And then these 3 remaining parameters are called the non-core group of parameters, and we will divide these among the 3 equations. So for the first one, I'll put the diameter, second one, diffusion coefficient, and third one, mass transfer coefficient. And then we want to raise each of the core group parameters to a certain power that we will then solve for these variable exponents through solving a system of simultaneous linear equations. So I'll just choose, for example, A, B, and C for the first equation, D, E, F for the second, G, H, I for the third. You can choose any variables you want to use, but just for simplicity's sake, I just chose the first letters of the alphabet. So now we can come over here and we can solve a system of equations to solve for pi1. So coming over here, pi1 is equal to density to the A, velocity to the B, viscosity to the C, and then times diameter. And we want to write kilograms, meters, and seconds. We will create 3 different equations to solve for the 3 unknown powers in this equation. So we'll create an equation for kilograms, meters, and seconds, and we'll do so by using, again, the units on each of these parameters. So, for example, for density to the A power, density is in terms of kilograms per cubic meter. So kilograms, we'll have kilograms to the first, so we'll put an A there, and then meters to the -3, so we'll put a -3A here, and then no seconds, so there will not be an A term for the seconds equation. And then moving on to velocity, no kilograms. Meters is just +1, so plus B, and then seconds is -1, so negative B, and then viscosity, kilograms, so plus C, meters to the negative first, so negative C, and then seconds to the negative first, so negative C again. And then this non-chord group parameter, which in this case is the diameter, will just be a constant. So we'll put +1 in meters, since diameter is just in terms of meters. And then we'll set each of these equations equal to 0, and we'll solve them as a set of equations. So first thing I notice is that A plus C is equal to 0, so A is equal to -C. And then I can see that I can add these equations to eliminate B, since there's a plus B in this equation and minus B in this equation. So we'll get -3A minus 2C plus 1 equals 0. We can sub in A equals -C into the A term. So -3A times -C minus 2C plus 1 is equal to 0. So 3C minus 2C plus 1 equals 0. C is equal to -1. And then A is equal to -C, so A is equal to +1. And then -B minus C equals 0. So -B minus -1 is equal to 0. B is equal to 1. So then we will plug in these exponents that we solved for into this pi1 equation. So we get pi1 is equal to density to the first power, velocity to the first power, viscosity to the negative first power, and diameter, just diameter to the first power. So we get, then when we rewrite this, we get pi1 equals rho VD over mu. And I can notice right now that this is just the Reynolds number. The Reynolds number is equal to the density times velocity times diameter over the viscosity. And this is exactly what we have here. So this is equal to the Reynolds number. And we have successfully verified that this is an appropriate dimensionless group to use to describe the scenario. So I'm going to rewrite this equation over here. So pi1 equals Reynolds number, which is equal to rho VD over mu. And so now that we've done this, we can move on to pi2. And this will mostly all be the same as pi1, just replacing the exponents with the other exponents and the chord group, or the non-chord group parameter, as dAb instead of diameter. So I'm just going to rewrite this, and I'm going to just keep all of these signs here, and just rewrite the same equations with the different variables, since they all be the same, since the units did not change at all. Okay, So now that I have rewritten those in the terms of the different variables, the diffusion coefficient DAB has meters squared in the numerator, so we'll put a +2 in the meters equation, and then a -1 in seconds to the negative first, so we'll put a -1 in the seconds. So we can solve this just as we did the last equation. So we get D is equal to -f, and then once we add these two equations, the e's cancel out, so we get -3d minus 2f plus 1 is equal to 0. So we can sub in -f for d, so we get -3 times -f minus 2f plus 1 equals 0. So we get f plus 1 equals 0, f is equal to -1, and then -e minus -1 minus 1 is equal to 0. We get e is equal to 0 since these ones cancel out. And then finally, d is equal to -f, so d is equal to +1. Okay, so now that we have solved for these exponents, I'll rewrite this equation as well. So we get pi2 is equal to density to the first, velocity to the 0, viscosity to the -1st, and the diffusion coefficient DAB. So I'm going to rewrite this. Pi2 is equal to density times the diffusion coefficient all over the viscosity. So I notice now that the Schmidt number is equal to the viscosity all over the density times the diffusion coefficient. So that's the reciprocal of this dimensionless group that we found here. So pi2 is equal to 1 over the Schmidt number. So the Schmidt number is an appropriate group as well to use to describe this scenario. So I'm gonna rewrite this over here. Pi2 is equal to the 1 over the Schmidt number, which is equal to rho times DAB all over the viscosity. Okay, so we've determined that two of the dimensionless groups described in the original scenario are correct and applicable to the situation. So now we just have to solve for pi3. So again, this will be similar to the process that we used to solve for pi1 and pi2. I'll replace the exponents and the non-core group in this equation. And the rest will remain the same since, again, the units do not change. I'll just need to change the non-core group. And the exponents are g, h, and I that we defined earlier, and the non-core group parameter in pi3 is the diffusion or the mass transfer coefficient Kc. So we have g plus I is equal to 0, -3g plus h minus I plus 1 is equal to 0 since the mass transfer coefficient has meters to the first in its units. And then we have no seconds, -h minus I, and then there's negative seconds to the negative first in the mass transfer coefficient. So we have a -1 there. And we'll solve this. G is equal to -I, and then we can add these two equations. The h's cancel. We get -3g minus 2I equals 0. We can sub in negative I for g, so negative 3 times negative I minus 2I equals 0. I is just equal to 0, therefore g is equal to 0. And then negative h minus 0 minus 1 is equal to 0. So we get h is equal to negative 1. Yep, h is equal to negative 1. So when we rewrite this equation, we get pi 3 is equal to rho to the 0, velocity to the negative 1, viscosity to the 0, and the mass transfer coefficient kc to the first. So we get pi 3 is equal to kc over the velocity. So the remaining group that we haven't defined yet in the initial problem statement is the Sherwood number, which the Sherwood number is equal to the mass transfer coefficient Kc times the diameter all over the diffusion coefficient dAv. This is not what we have right here. However, the units of the diameter over the diffusion coefficient, diameter is in units of meters, and the diffusion coefficient is in units of meters squared per second. And when you divide that, you get 1 over meters per second, which is the same as 1 over velocity that we have right here. So we can determine that the Sherwood number is an appropriate group through the units canceling out right here. So pi 3 is equal to the Sherwood number, which is equal to Kc over velocity, which is equal to the mass transfer coefficient times the diameter all over the diffusion coefficient. And that's all. We've determined that the Sherwood, Reynolds, and Schmidt numbers are the appropriate dimensionless groups used to describe this scenario, and we can move on from there.